Hey, good morning and welcome to the 2017 International Academy of Astronautics Planetary Defense Conference, Gathering for Impact. Interesting choice of words, I think you'll have to agree. I'm Bill Ayler from the Aerospace Corporation. I'm chair of the conference, and I'd like to introduce my two co-chairs. First is Mr. Brent Barbie, the National Aeronautics and Space Administration. Brent, where are you? Okay, very good. And also Dr. Gerhard Drolshagen, who recently retired from the European Space Agency and is now affiliated with the University of Oldenburg in Germany. Gerhard, over here in the dark. Okay. The conference chairs were aided by members of the conference's organizing committee who provided advice and counsel over the last year. If you're a member of the organizing committee, if you could please stand, and this is all those who participated in our telecons for the last 12 months. Very good. And I just want to say thanks to all of you for the help you've given and advice and counsel, and I hope you'll see it reflected in the conference as we go along. Thank you very much. Let's see. I also want to introduce and thank the chair of the local organizing committee, this Dr. Makoto Yoshikawa of the Japan Aerospace Exploration Agency. Dr. Yoshikawa did heroic work in arranging the local support for this and also arranging for this magnificent facility for this conference. So I think we should give Dr. Yoshikawa a hand. Hey, there he is. Good. He was also assisted by members of the local organizing committee. And if you're a member of the local organizing committee, could you stand to be recognized? I think most of those people are wandering around outside registering people and so forth, so we'll get a chance to do that. And again, I just want to thank also the Japan Space Guard Foundation and the Japan Space Guard Association. Interesting, I thought was just looking on the web to see what they do, and their mission is to protect the Earth's environment from a disastrous near-Earth object collision by studying and observing the NEOs. We sincerely appreciate their help and involvement in making this conference a success. So again, thank both of those organizations as well. Okay, so basically, as you know, this conference is one of those that's offered by the International Academy of Astronautics, and we're honored to have Dr. Hiroki Matsuo, Vice President of the IAA, to give a quick overview of that organization. So, Dr. Matsuo, yeah.
Well, good morning, ladies and gentlemen. I am Hiroki Matsuo, Vice President of the International Academy of Astronautics. And as I am here representing the Academy to give a brief description of the Academy would be in order. Though I am known as a fluent speaker of Japanese, but my English is quite poor. So hereafter, please guess what I mean. The Academy was founded in 1960 by Theodor von Karman, one of the space pioneers. Its membership consists of individuals elected by members voting in recognition of the individual's record of service and achievement. And the purposes of the academies are, sorry, as I am not good at remembering this kind of important but boring sentences, I would like to read it here. First, to foster the development of astronautics for peaceful purposes. Second, to recognize the individuals who have distinguished themselves in a branch of science and technology related to astronautics. To provide a program through which the membership can contribute to international endeavors and cooperation in the advancement of aerospace science in cooperation with national science or engineering academies. About 1,200 members and corresponding members belong to either of four sections: basic science and engineering science, life science, and finally the social science, covering all the area of the space science research areas. Besides organizing symposia at the ISE, that is International Astronautical Congress, as a co-sponsor of the Congress, the most important activities of the Academy is to form study groups and work on various topics and to publish their results. To give some idea the scope and the nature of these studies, I will cite some examples, very few examples. Say, space debris environment remediation, or the architecture of space, tools for development in the 21st century, space expectation shaping the next 50 years, something like that. And at this moment, 45 studies are in the works. Regular journals is Acta Astronautica, 2,000 pages a year, which covers space science and technology related to the peaceful use of space. In addition to regular issues of these journals, consisting of contributed papers, the journal publishes special issues devoted to selected proceedings of Academy, symposia, and conferences. While becoming a member itself shows that he or she is recognized as an expert in this field, the Academy has an active program of award in order to promote excellence and recognize the achievement of our members. Most prestigious one is the von Karman Award, after the name of founder of the Academy. So another award, the Laureates for Team Achievement, in 2016 went to the New Horizon team, Pluto mission team. As another important activity of the Academy, in 2015 to 2016 time frame, 16 so-called standalone conferences and workshops were organized, and some jointly with space agency or university from various countries. This planetary defense conference is one of this so-called standalone conference of the Academy, which started in 2009 in Canada. I have been with Japanese space activities so long that I put on the firing switch of the Japanese first satellite launching in 1970, not as a flight director, but just a panel operator. In those days, our nightmare was that the vehicles we launched by ourselves might hit the surrounding populated area. Of course, due to various kinds of malfunctions. Fortunately, we did not see the casualties, but this range safety constellation has been very important and sensitive issue of the launch operations. Now, the impact of NEO impact could far exceed those caused by artificial objects. To face this, we need further derivation and research work in technical, social, and political areas, such as covered in the program of this conference. I am glad to hear that the project in this field are currently funded or being conscientiously considered for funding by the governments or the agencies of some major space-faring countries. Though it's a pity that I find only one Japanese name on the list of participants of Frascati, this conference is an excellent opportunity to provoke much stronger interest in the Japanese space community and in public. Finally, in advance, I congratulate you, the members of organizing committee, on the success of this conference in advance. And please enjoy your stay in this safe city. NUO impact during this conference period, it's not forecasted. Thank you.
Okay, thank you, Dr. Matsuo. Okay, I think you'll find that our planet has the capabilities required to deflect a threatening object, but two things are critical to doing that successfully. First, we must have time to act, and this means we must be able to find these objects early. Second, our leaders must make some difficult decisions if we're able to successfully deflect a threatening object. Given that, we're honored to have an elected official here, the Honorable Hajime Funada. He will be providing some welcoming remarks. Mr. Funada is a member of the House of Representatives of the Diet, the National Legislature of Japan. Mr. Funada.
Good morning. My name is Hajime Funada, a member of the House of Representatives of Japan. Professor Hiroki Matsuo, distinguished delegates, it is my great pleasure to host the 2017 Planetary Defense Conference here in Tokyo for the first time in Asia. About 65.5 million years ago, at the end of Cretaceous period, more than 70% of the species, including the dinosaurs that were in prosperity at that time, were extinct. The reason for this extinction has been a mystery for a long time. In 1980, Luis Alvarez and his son Walter Alvarez proposed a sensational hypothesis. They insisted that the mass extinction was caused by a collision of a 10-kilometer-sized asteroid to the Yucatan Peninsula in Mexico. In 1994, comet Shoemaker-Levy number 9 collided with Jupiter before our very eyes. This event also strengthened Alvarez's hypothesis. After this event, the International Space Guard Foundation and Japan Space Guard Association were successively established. During the construction of the Subaru telescope, I became acquainted with the late Professor Isobe. Professor Isobe became the first director of Japan Space Guard Association, and so I also attended the association. The Japan Space Guard Association is supporting the Bisei Space Guard Center, where asteroid discoveries and orbit calculations are carried out. Now this field is being caught up in space situational awareness, which deals with space debris, an important but distinct topic. I am anxious about the future activity of Space Guard. The probability of a collision that threatens the existence of human beings is very small. However, if such a collision occurs, it will become a threat not only for humans, but for all the lives on Earth. Therefore, we should invest appropriate manpower and budget. The public have shown an interest in this issue from movies such as Deep Impact and Armageddon, and we must focus on fostering a continual interest in the issue of asteroid threats. I sincerely hope that all of you who have gathered at this conference will find promising situations to this issue in order to keep this beautiful nature and human beings on the earth forever. Thank you.
Thank you very much. I just want to say that we all know that from the technical standpoint, we could actually do something, and I think it's very important to make sure that we have the public and our elected officials supportive of this concept as well, and thank you again for your comments. As you know, any effort to deflect a threatening object will require us to launch spacecraft to get a good idea of the size and other characteristics of the object, and if necessary, to launch missions to deflect the object away from Earth. Space agencies worldwide would be involved. We are most fortunate to have leaders of two space agencies whose successes have significantly improved our knowledge of asteroids and comets here today to provide conference keynotes addresses. The first is Professor Saku Tsuneta, Vice President of the Japan Exploration Agency and Director General of JAXA's Institute of Space and Astronautical Science. The Institute has proposed and executed a series of ambitious projects, including the Hayabusa mission, which landed on an asteroid, collected samples of asteroidal material, and returned those to Earth in 2010. Agency, the ISAS, is also played an important role in Hayabusa 2, which will collect samples from another asteroid and return them to Earth in 2020. As is evident, ISAS has been taking a major role in space science research alongside NASA and ESA. So please join me in welcoming Professor Saku Tsuneta. Professor? Good morning. Here you go.
Okay. Do I have my presentation? I think it is our great pleasure to see that the 5th IAA Planetary Defense Conference is being held in Japan. Using this opportunity, let me briefly introduce JAXA's space science activities and plan for future, especially in planetary science, which would be directly and indirectly related to planetary defense. It will come, okay. I see my slide here, but not over there, and I should wait for a while. First of all, I want to introduce ISAS, Institute of Space and Astronautical Science, which should appear here. Could someone take care of this? Okay. Maybe let me continue. As a National Center of Space Science and Engineering Research, ISAS carries out development, launch, and innovative operation of space science missions with other directorate of the JAXA. ISAS is an integral part of the JAXA and has close collaboration with other directorates such as Research Development and Human Spaceflight Technology Directorate of the JAXA. As an inter-university research institute, these activities are intimately carried out with universities and research institutes inside and outside Japan, and ISAS always seeks for international collaboration. And space science missions are proposed by researchers and incubated by ISAS, and ISAS plays a strategic role for mission selection, primarily based on a bottom-up process, also considering the strategy of JAXA and the national space policy. And I really need a slide at this point. So maybe I should wait. Oh, finally appears. Thank you very much. So I read this part, so this is finished. So let me continue. These are recent science missions ranging from astrophysics missions, such as infrared, X-ray astronomy, and solar missions, to planetary missions such as Venus Orbiter, Lunar Mission, UV planetary observation, and of course, Hayabusa 1 and 2 mission. And there was also solar sail mission, Icarus, which is a technical demonstration of a solar sail technology. One uniqueness of ISAS is the very close ties between space science and space technology. And the Space Technology Division, consisting of spaceflight systems and spacecraft engineering. And the Space Science Divisions, consisting of space astronomy, astronomy and astrophysics, solar system science, and interdisciplinary science interacting very closely in a bilateral way. Namely, science often stimulates and encourages new technology development, and this is a science-driven approach. Vice versa, technology sometimes leads and creates space science programs. This is the technology-driven approach. One superb example for technology-driven approach is the first interplanetary microsatellite called Procyon. This 65-kilo probe carrying ion engine took beautiful neutral hydrogen geocolumnar images from away from the sun since Apollo 16 in 1972. So this is the imaging, the Lyman alpha image taken by this small satellite. Another recent accomplishment are Hayabusa and Icarus missions, which are driven by ISAS engineering faculty members. And Japan's contribution to Space Guard includes, of course, Hayabusa 1 and 2, as I describe later a little bit, with Bisei Space Guard Center, ground-based telescopes such as Subaru Ultra-Wide Field Camera, and Asia-Pacific Asteroid Observation Network. Let me point out one very significant example of the contribution from space science to the planetary defense. Hayabusa 1 changed the concept of small NEO, near-Earth objects. It shows that asteroid Itokawa consists of a rubble pile, and this discovery would be important for space guard considerations. We are very happy to see that both Hayabusa 2 and NASA's OSIRIS-REx are in good shape. And Hayabusa 2 was launched in 2014. Let me show you this. With its arrival at Ryugu in 2018, and its departure will take place in 2019, and arrival on Earth in 2020, the year of Tokyo Olympic. Almost in parallel, NASA's OSIRIS-REx was launched in 2016, with its arrival at the Bennu in 18, departure 21, and return on 23. So we plan to have a very extensive collaboration with NASA's OSIRIS-REx for operation and joint sample analysis. And one viewpoint for such collaboration is that since sample and return is a high-risk mission, even everything is perfect, something potentially happens. The collaboration, which includes a sample exchange between NASA and JAXA, serves as a means for insurance for both science teams. I do not need to go into the details of the mission scenario of Hayabusa 2, but one notable feature that may be related to SpaceGuard is that the impactor ejected from Hayabusa 2 collided with the asteroid, creating an artificial crater. The plan is that the fresh sample not turned by solar illumination will be obtained from the newly created crater. And this is a very interesting experiment. We'll see what will happen in a few years. So beyond these ongoing missions, we see on the horizon the multiple missions candidates to be launched in later half of the 2020s. And let me look at the future and see missions emerging on the horizon. So this is the overall situation of the Japanese science program. And the government is very generous in the sense that the Space Policy Commission and the Cabinet Office intends to guarantee predetermined steady annual budget for space science and exploration to maintain its scientific activities. This allows us to develop a long-term plan and international collaboration. There are three different categories here. The first one is strategic large missions for JAXA-led flagship science missions to be launched with H2A or H3 vehicle. The cost cap is about $300 and $350 million equivalent, including vehicle cost. So we'd like to have 3 such missions in 10 years. And competitively chosen medium-sized focused mission, the cost is under $150 million, including vehicle, will happen every other year or 3 years, and this will be launched Epsilon solid rocket. We also have missions for opportunity for foreign agency-led mission. So strategic large mission here start with the X-ray astronomy recovery mission to be launched in around the 2020s, followed by the Martian Moon Explorer called MMX to be launched in 2024, leading to the infrared big observatory called Spica closer to the end of the decade. Between MMX and Spica, we like to put either a mission for cosmic microwave beam detection called LightBird or solar power cell mission. Its technological demonstration was, as I said, beautifully done by JAXA's Icarus mission. Its declared destination is the surface of the Trojan asteroid of the Jupiter system. And competitive M-class mission successfully started with Hisaki and Arase observing the Jovian and Earth radiation belt respectively. This will be followed by an engineering pathfinder mission for precision landing on the moon called SLIM to be launched around 2020. I hope this would pave the way to send major science missions to land on the moon and other planets. A probe called Destiny Plus is under serious consideration for New Start and implementation. Its primary purpose is to measure the properties of interplanetary dust and route to the asteroid Phaeton with technology demonstration of a small probe for interplanetary flight and its eventual flyby of the asteroid. And JAXA's mission to the Martian moons, MMX, will make a close-up remote sensing and in-situ observations of both moons and return samples from the Phobos. And JAXA is developing MMX with significant contribution from NASA and French CNES for the launch in 2024. So let me put MMX and other planetary missions into perspective. Small bodies born outside the snow line, initially comet-like, evolving in time to show various phases. Water and organic compound delivery by these may enable the habitability of the planets such as Earth and early Mars, maybe. A keyword connecting these missions is a delivery of water and organic material to Earth. And the question is when, who, and how. And ISAS plans to address these questions by the series of small body missions. And this chart shows our approach to planet and asteroid with international partners. We go to near-Earth objects such as Moon, Mars, near-Earth asteroid by ourselves. Beyond that, we will work with international partners and friends which have access to those distance targets such as Mercury and Jupiter. And let me stress that ISAS always seeks for international collaboration. Most of our astrophysics and planetary missions as a result of the intimate international collaboration, especially with ESA and NASA. The most recent example is our participation in the JUICE mission led by ESA. The JUICE mission is a mission to the Jupiter and its moons. Very good mission. So let me briefly mention the ESA-JAXA Spica mission, which are under review in ESA M5 competition. And the Spica is a 2.5 meter aperture infrared telescope, cooled down to below 8 Kelvin. Its core observing wavelength is near infrared to far infrared. Spica will be put in Sun-Earth Lagrangian 2 halo orbit by JAXA's H3 vehicle in 2028 timeframe. One unique property of Spica is its unprecedented sensitivity as compared with the telescopes in orbit and on ground in the 2020s. Let me point out that the Spica is a powerful mission in terms of the planetary science. One of the big questions in the current astrophysics is when and how does gas evolve from primordial disk into emerging planetary systems? How do ice and minerals evolve in the planet formation era as seeds for solar system? The Spica's approach is twofold: detailed study of protoplanetary and debris disk in extrasolar system to shed light on the history of our system, and observation of planet and minor bodies in our own solar system to characterize the early solar system and its evolution to the current system. And more concretely, Spica will make a systematic observation of the deuterium ratio of comets, which is quite interesting topic in the current planetary science. And comets, the most primitive bodies in the solar system, and thereby quantify the original water characteristics in the early solar system. The Spica will also detect hundreds of the trans-Neptunian objects, which are expected to bear unaltered records of the formation and evolution of the outer solar system. Spica will infer their composition by measuring their size and albedos. Spica will also have a spectral resolution 10 times better than those previously exploration missions in the mid-infrared, which contains the key features of critical molecules and will reveal the detailed composition and structure of the planetary atmosphere. So ISA's minor body exploration strategy map has to be revised to something like this to include the very significant potential contribution of the Spica mission in the late 2020s. Finally, changing the topics to the planetary defense, I have to say something about planetary defense, of course. Let me finally mention our awareness of the danger of the rare but catastrophic events such as the collision of asteroids and comets. Let me talk about myself. Before moving to JAXA 4 years ago, I spent about for 40 years as an astronomer studying the sun from space. Thus, I think it's my prerogative to talk about the sun a little bit before concluding my talk. So a question here is, what is the largest solar flare? The explosion on the surface of the sun due to magnetic connection produced largest solar flare produced by the sun. And Richard Carrington, an English amateur astronomer, observed the largest solar flares ever observed. The very bright aurora appeared in next day in Cuba, Bahamas, Jamaica, El Salvador, and Hawaii. So this tells us how big the flare is. So we call flares many orders of magnitude larger than the largest solar flare ever observed, super flares. super flares. Then the question is, did super flares ever occur on the sun? And if the answer is yes, how large were they? And the Kepler serendipitously shows that stars are prone to what we call super flares. Occurrence of such events would be extremely rare if we concentrate one star, but with over 100,000 stars simultaneously observed by Kepler, many super flares have actually been detected by the effort of the Professor Shibata of the Kyoto University. So this particular example shown here shows the super flare with a total energy of 10 to the 36 ergs, 10,000 times larger than the largest solar flare ever observed. And let me go on. This is the energy size versus occurrence rate diagram. We see that the larger flare, the less often it occurs. Super flares observed by Kepler are much larger than those solar flares, but they are on the same line, extrapolated from the observed solar flare range. This shows that even in the sun, a super flare 10,000 larger than the biggest observed solar flare can happen every 5,000 years. So 10 to the 37th erg super flare may occur in every 1 million years. The super flare of this magnitude may cause the ozone depletion, very serious ozone depletion, and disaster for civilization. So this is a space flare research. And societal effects of flares and super flares have been one of the very important topics in the solar and heliophysics. The occurrence rate and its impact to humanity of super flares appear to be quite comparable to those of the asteroid collision if we compare these numbers. And I must say that the Great East Japan earthquake that took place in 2011 resulted in 15,000 deaths and the meltdown of the Fukushima Daiichi nuclear plants. This earthquake, the earthquake of this magnitude happens every 5,000 and 50,000 years, depending on the literature. The numbers are scattered. But this indicates that, these examples indicate that we should be prepared for the catastrophe, even with this level of extremely low occurrence rate. So I fully agree with the concept of the planetary defense. Let me summarize my talk. JAXA appreciate and respect consolidated efforts so far made by various organizations and individuals for planetary defense. And possibility of catastrophic asteroid collision is comparable to those super flares, which has been discussed very seriously in astrophysics community and the major earthquake as we observed some years ago, and should be by no means be neglected. JAXA's space science has been contributed to the planetary defense directly and indirectly, as I have shown, and will continue to do so in the future. Thank you very much.
Thank you, Professor Tsuneta. Our second keynote will be presented by Johann-Dietrich Woerner, who became the Director General of the European Space Agency in July 2015. Prior to that appointment, he served 8 years as chairman of the executive board of the German Aerospace Center, was head of the German delegation to ESA, and was chairman of ESA's council for 2 years. As you know, ESA's Rosetta spacecraft provided some outstanding images while it orbited a comet, and in 2014, its lander, Module Philae, performed the first successful landing on a comet. Please join me in welcoming ESA Director General Jan Woerner.
So, I hope everything will work now. At least I have some hope, and therefore I do it myself. Then it's the easiest one. Okay. So, ladies and gentlemen, it's a great pleasure for me to be here and to talk a little bit about planetary defense, and especially I would like to welcome in Japanese also Funada Kukai-jin, because what you were said, and I will come back to what you said, it's very important for me. So I will talk about planetary defense, and I will talk about it, which is directly linked to what we heard right now, and this is, the first thing is the question of probability and damage. You could say also likelihood and severity, so whatever you take. So risk, and we are talking about risk, if we are talking about planetary defense, we should really understand that risk is the multiplication of probability of something happening times the amount of damage, as we heard in the last presentation as well. So it's very similar to that. And if we look to this picture, then you see here, it is the amount of damage over here, it's probability over here, and this line shows now a constant risk. To make it a little bit easier, and also coming back to the last presentation, if we look on a log-log scale, these are straight lines. Now the only thing is, and this is the most complicated one, to define a line where we are all happy with. And so I make it easy here because I give no numbers. So let's say this is the acceptable risk. But if we have the acceptable risk, then the next thing starts, meaning whatever is above acceptable risk is not acceptable, and the one below is not. So far, so easy. But now the real issue comes, and we heard that also in the last presentation. We have to look to the different things which may happen and to the consequences. So if we are talking, for instance, about mankind is endangered, then of course, because it's a big amount of damage, we need a very, very small accepted probability of this happening. If we are talking about just a test, and we are doing tests also in space, then of course we can accept a much higher probability. And unfortunately, people are not thinking in that way. So I was very happy that your parliamentarian here from Japan was mentioning this already with probability. Usually what I'm learning is that politicians, I have to apologize, politicians don't care about these things because the probability, let's say 1 in 2,000 years, 1 in 50,000 years, they will say, it's out of my term, so I don't care about that. And therefore it's important that, as you mentioned it correctly, Funada-san, that we take care of it because the consequences might be so big. And we should at the same time accept also when we are discussing in space about tests we are doing, that their failure is acceptable because it's just a test. And in between we have different things. So individuals, maybe the victims, or security-related systems might be of, as we heard, for instance, electricity and other things. So there is a difference then in the amount of damage, and therefore also a difference in the acceptable probability. Now, if we are talking about planetary defense, usually we are talking about near-Earth objects coming towards the Earth. But at the same time, of course, we have now an issue also with space debris. We have about more than 750,000 particles of a size of at least 1 centimeter. And therefore, as they are all flying in vacuum, what we need is a vacuum cleaner. So we need a vacuum cleaner to get rid of this problem. And this is also endangering us on Earth. It's not only that the asteroids or meteorites are endangering us, so also these particles are endangering us. So you know the movie Gravity. I liked it because of Sandra Bullock, but it's also, and there were some mistakes in the movie, but some other things were very serious. For instance, the effect of space debris towards such a spacecraft. But also, you see, when I'm talking about damage, we should look also to our spacecraft. This is Sentinel-1A, one of the European satellites for Earth observation, a radar satellite. And in 2014, we launched it, and we had a nice view on the solar panels. And some 2 years later, suddenly, the electric production declined, and we used the camera again, and we saw over here an impact of a very tiny debris, but it has already a much bigger consequence because the electricity went down. Still, it's enough for the satellite, but we have to see that also small parts can destroy us. And also, of course, when we are talking about rockets and the different parts of rockets, some of them might fall down again. And then it's a question, is it planetary defense, or how would you call it? I can tell you that people affected by that, they would not care about how we call it. If they are affected, for instance, in this case, So upper part of one launcher fell down into this house. I can tell you the farmer was not happy at all, and he did not care, as you see it from his face, whether it came from an asteroid or from a rocket. It's just he wanted to have a protected home. So planetary defense for me has a wider range than just the question of asteroids and meteorites. Another thing, another example is this satellite called ROSAT. This was a German satellite together with the Americans and the British. It was launched, and originally it was planned it should be launched with a space shuttle. Unfortunately, because of the accident of a space shuttle, it was not launched by a space shuttle but by a normal launcher, and therefore it could not be deorbited afterwards directly or brought back by a shuttle. But before that, it was a very successful mission. It has a lot of scientific results, and also the varifocals. The method of how to produce varifocals comes from this satellite. So it was a very successful launcher and a successful spacecraft, but then it deorbited by itself, and we were very much afraid, and this was worldwide because of ceramics inside the satellite and glass. We were sure it will survive the re-entry, and you see here the last orbits, and you see one was very close to Japan over here, and this one over here. And this was the very last one, and I can tell you that these were one of the most difficult times for me in my life to follow this satellite, and I was responsible for the German Aerospace Center at that time. And the question was, okay, where on this line it will fall down? Over here or over here, Beijing. So you could have many places. We were very lucky it fell down over here. Nobody was hurt, at least nobody we know about. So this was rather bad, but again, this is also something we have to protect. The insurance companies are now using this already for their advertisements and saying, yes, we help you in those cases. But again, this does not help the people themselves. And we had collisions of spacecraft in space with Iridium and Cosmos producing even more parts in the orbit. And for the future, we are talking about mega constellations with several hundreds or even thousands of satellites. And I'm a bit afraid about that, because they are already saying that they are designing these spacecrafts so that they have at least 90% working positively. That means they are accepting 10% to fail. 10% to fail, if you have 4,000 satellites, means another 400 space debris. And this is, for me, a very difficult thing. So we have to solve this issue as well. We need, for the future, very clearly, a satellite collision avoidance system like we have in planes. So this is, for me, one of the very important issues we have to develop. Now, if we cannot handle the old satellites any longer because of whatever happens, sometimes even if you have a very nice deorbiting concept, if the spacecraft is by a small particle hit and is losing all its operationability, then of course you have to do something afterwards, and it is very difficult to get the funding for those type of maintenance or deorbiting, because to buy a new satellite, you get the money immediately. But just for the waste, to put the waste away, it's at least for us in Europe, it's rather difficult to get the same amount of money. And then we have, of course, these effects like in Chelyabinsk in 2013, and this was a tiny one. We had about something like 2,000 people hurt by that only, so it was really nothing big. And also the final impact over here in a lake, lucky enough, was not a big one, so one can say this was not a big problem. But we know that there were bigger meteorites and asteroids coming towards the Earth. For instance, this crater in Arizona some 50,000 years ago is much bigger, and of course we discussed already, heard about the dinosaurs, the dying out of the dinosaurs, most probably due to an impact of some meteorite. And you see here, these are the 174 confirmed impact craters worldwide. So there is really every location on the world is or was hit in the past by some meteorites. So it is beyond all the calculation of probability there is really a chance that we will be hit by another one, and it means that we also have to be aware of it. And this one, asteroid 2017, AG13, was very close to the Earth, and it slipped through our Earth's defense. So we did not see it before. It had just the distance of half of the distance to the Moon. So it was really close to the Earth, and it was discovered just shortly before. And so we do not have so far any means what to do then, and therefore it's very bad. And something like this, if this happens, we should not be really happy. Then this is really a complicated situation, and we should not believe, okay, we can escape to the Moon and have a nice view from the Moon, so what is happening on Earth, we don't care. And I can also tell you that Bruce Willis is not ready to do it again. He did it once, and this was enough for him, so he will not do it again. So we need something to solve it. And we tried to develop something as a first step together with our colleagues from NASA. So it's a mission consisting of 2 missions, AIM and DART. So the idea was that we fly to an asteroid, Didymos, and there is a small moon called Didymoon. And so that while we are observing and doing some science with these 2 bodies, that the NASA spacecraft would even hit the Didymoon, and that we can see what is happening with the deflection and knowing all the characteristics of the Didymoon before by our AIM mission. Unfortunately, we could not succeed in the first round to get the funding from our governments directly, because I'm totally dependent on what my governments, my 22 member states, give me for a certain project. So last year we did not really succeeded in getting this money in the very first round, but we are still working on it. We still have several member states being interested and able to pay some money, and we are looking also for some industrial partners who would join. So I think this is something where we can and we should in the future go further on. And as it was mentioned, we have different aspects. I'm also mentioning here the space weather, of course, with the solar flares. And we do not have to look just for the big effects of solar super flares, but also the smaller flares are changing already the electron flux in the ionosphere, and therefore changing the accuracy, for instance, of navigation signals. So it is all about space debris, space weather, and near-Earth objects we have to take care about. And as I mentioned earlier, I think this is a real point where we have to work globally together and not just on a national basis. Because on a national basis, you can always say it's not our waste in space, so therefore why should we take care of it? But I think all our spacecraft are endangered, and also the humankind is endangered by near-Earth objects, so we better do it together. So for space debris, of course, tracking, collision avoidance and removal is necessary. For space weather, monitoring and forecast, we cannot change it, unfortunately. And for near-Earth objects, detection, prediction, and to define and develop countermeasures is of utmost importance. And my clear plea is we should do this in a global cooperation scheme, because otherwise it will not work. This is a too big challenge for one country. And ESA is already an intergovernmental and international organization with our 22 member states plus Slovenia plus Canada. We are ready to really play an important role in this. We believe that this is important for all of us, and therefore let's look for it. And we have some experience worldwide to cooperate, for instance the International Space Station, or for instance the International Charter for Space and Major Disasters, where we are working globally together. So why not do it also in planetary defense, and to create an alliance for the detection, risk assessment and mitigation, because all 3 aspects are important. We should not only predict and detect, this is nice, but then to know that something happens, what will you do afterwards? So we better develop also methods of risk mitigation, of countermeasures against any near-Earth objects coming toward the Earth. With that, I would like to finish. Thank you very much for your attention, and I'm looking forward really to create this global alliance. Thank you very much.
Okay, thank you, Dr. Woerner. That was a very interesting and inspiring talk, and I think woke us all up. That's very good. Okay, with that, we now have a short break, and so we'll have refreshments. And Makoto, where will they be served?
Okay, so the coffee is served in the room of Uranus and Saturn. Okay, Saturn and Uranus is a coffee break room, and it is just in front of the poster room.
So basically, it's just down the hall, right in front of where the posters are. And if you want to see the poster facility, it's just beautiful there. So we'll see you at 10:20. Thank you.